Alright, here's the video for the key for your review worksheet for Chapter 3, I guess Unit 10. We're going to write a function. We have a quadratic function, and we want to turn it into vertex form, and then graph the function by starting with the graph of y equals x squared, which is our parent function. So that's the parent function, and then transform it, either shifting, compressing, stretching, or reflecting. So there's a couple of different ways you could do this. The first way that I work with is completing the square. So we rewrite this so that 0 is on one side and our function's on the other. And then I add 1 over. Okay. 1 equals 1/2 x squared plus x. You can have a space and a space. Then I want to factor out a 1/2 from x squared. Well, that's going to turn x into 2x, because what you've really done is you've done 1 over 1/2 for that middle term, which is the same as 1 times 2. Okay? And then we want to space it out, and we're going to complete the square. We're going to take 2, our middle term, divide by 2, and then we're going to square it. Well, that becomes 1. So I'm going to add a 1 in. But this 1 is being multiplied by 1/2, so I have to add a 1/2 over here as well. Okay? Again, this 1 here is being multiplied by this 1/2. Still, if you distribute it through, so you add the 1/2 over. Alright? So on our left side, we end up with 3/2 equal to 1/2 times, and then we're going to factor this and rewrite it as a square of two binomials. So we have x plus 1 quantity squared. Right? And we know it's plus 1, we know it factors to that because when we divided by 2 and squared it, we got a 1. Whatever we get before we square it, 2 over 2 was 1, that's what goes in here. So if it had been like negative 2 over 2, well then we'd have x minus 1 squared. Alright, and then we're going to subtract the 3/2 back over so that we have our final function. So this becomes our vertex form that we were looking for. So that means that h equals -1 and k equals -3/2, and a, the coefficient in front, is 1/2. Well, this is telling me right here that we're going to sort of stretch and flatten out our parent function. So we're going to start with our parent function. And a parabola always has, when it's just y equals x squared, if you plug in 0 for x, you get 0 for y. If you plug in 1, you get 1. If you plug in -1, you get -1. So right now I'm doing y equals x squared. Then I'm going to do y equals 1/2 x squared. And then I'm going to do our final guy. And so maybe what we'll do is we'll do our stretch in red and then this guy in blue to finish it off. And we'll start in black. When I plug in 2, I get 4. 2 into y equals x squared is 4. Point. -2, same thing. So we kind of graph like that. Alright? And they mirror each other. Not the most perfect mirroring there, but you know, you get the picture. Alright, so then we want to shrink this or stretch it by 1/2. So that means when I plug in 0, I still get 0. But when I plug in 1, I'm at 1/2. When I plug in 1 over here, I'm at 1/2. When I plug in 2, I get 2. So what we're showing is the kind of new shape of our function. When I plug in 3, I get 4.5. So what's happening here is that because of the 1/2, we're slowing our growth by half. And we're kind of widening the mouth of our parabola. Right? One thing to note is that if this had been, say, I don't know, 4, we would be skinnier. We'd be right in here somewhere. But it's not, so we're sticking with what we got. Okay? And then whatever happens after you've created this sort of second graph here, our red graph, everything else is just shifting it either right or left or up or down according to our H and K. So now we're going to take a look at this guy. So H was -1, which means we're going to shift to the left 1. So 1 unit left. And then it says down 1.5. So we're going to be, our vertex is going to be right around there. Alright, let's see. Then we want to shift all of our points the same. So we're going to take this point here, we're going to go left 1, down 1.5. We're going to take this guy and we're going to go left 1, down 1.5. And so now I've got the left side of my parabola. I know that I have an axis of symmetry right here at x equals -1. And so I want to find points that are equidistant from this axis of symmetry. So looking at this point here, I'm at 1/2 for a y value, and I'm 2 units from my axis of symmetry. So I know that I can go 2 units to the right, place a point, and get it going. And there I go. Okay? So the blue guy is our final graph. Final. One we were looking for all along. And our new vertex, I'll label at -1, -3/2. You could have used x equals -b over 2a to give you this, and then plug that back in to our original function to get this, and then written y equals a times x minus h squared plus k based off of that and solved for a. But I think this is the better way to do it. Okay, now we have another parabola here in standard form, and we want to know, does it go up or down? So I look right at the coefficient. Is that positive or negative? It's positive, so we're going up. Then I want to find the vertex. So I'm going to use x equals -b over 2a, and I get 2 over 2 times 4, which equals 1/2. Oh, excuse me, 1/4. So my vertex starts at 1/4, and I just need to figure out what the y value is. So I'm going to plug in, I got 4 times 1/4 squared minus 2 times 1/4 plus 1. So I get 1 over 16 here times 4. That's going to be 1/4. Bring it down here. 1/4 minus 1/2 plus 1. So we really got 1/4 minus 2/4 plus 4/4. So I got 3/4. So 1/4, 3/4 is our vertex. Our axis of symmetry, x equals 1/4. And our x-intercepts. Our x-intercepts are going to be what makes this thing go to 0. So I'm going to factor. Oops. A little factor refresher. We're going to take 4 times 1, set that here, and we need to add to -2. Well, 1 and 4 and 2 and 2, neither of these factors have a difference of 2, whether positive or negative. This has a difference of 3, or it adds to 5. This has a difference of 0, or it adds to 4. So this can't be factored. So then I need to use x equals opposite b plus or minus the square root of b squared minus 4ac all over 2a. Okay? And I plug in x equals 2 plus or minus the square root of negative 2 squared minus 4 times 1 all over 2 times 2. And we simplify this. We get 2 plus or minus square root 4 minus 16 all over 4. So we end up with 2 plus or minus square root of negative 12 all over 4. And what we start to see is that I have a square root of a negative. That means that this entire thing is going to be imaginary. So there won't be any x-intercepts. The other thing you can notice is that our vertex right here is in the first quadrant, and we're pointing up. So if I were to draw that concept, let's see if I can erase some of this. Okay, so if I were to draw this, let's say 1's here, 1's there. So we're at a half, 3/4. Our vertex is here. Regardless of what else happens, it's at least going up, like that. So it'll never be headed towards the x-axis. So there couldn't be x-intercepts. Okay? So that's another way to look at it. For y-intercepts, I want to plug in 0 for x. F of 0 is equal to 4 times 0 squared minus 2 times 0 plus 1. This goes away, leaving leaving 1. So f of 0 is 1, so then 0, 1 is your intercept. Okay? Alright, so now we want to go backwards. We're given a function and we want to write it, and I want you to write it in standard because you're going to have to on the test. Alright. So we know our vertex is negative 2 and 6, so I can start there. Y equals a times x plus 2 plus 6. I've got a squared above. What we don't know a. We're not sure of x or y. But then we can look here. This is an x and a y that sits on the graph. So I can plug in negative 2 equals a times negative 4 plus 2 squared plus 6. Now my only unknown is my a. So negative 2 equals a times negative 2 squared plus 6. Subtract 6 over, I get negative 8 equals 4a. Divide by 4, and a equals negative 2. So then I can rewrite and say that y equals negative 2, x plus 2 squared plus 6. And then I can start to simplify. Y equals negative 2, x squared plus 4x plus 4 plus 6. Never square x and 2 and call it a day. You always need to FOIL when you have a binomial squared like you do here. Okay. Then we distribute our negative 2 in everywhere, so we get y equals negative 2x squared minus 8x minus 8 plus 6. And then this needs to be simplified to y equals negative 2x squared minus 8x minus 2. And there you have your function. Alright, so here we have a word problem. Let's read through it. A projectile is fired from a cliff 200 feet above the water at an inclination of 45 degrees to the horizontal. The muzzle velocity is 50 feet per second. The height of the bullet is given by the function h of x is equal to negative 32x squared over 50 squared plus x plus 200. Why plus 200? Well, our starting height is 200. Okay, so here's our cliff. Alright, and here's our guy, and he's shooting right here. And there is the height of the bullet. What point would that be, you ask? That would be your vertex, your maximum height. And they want to know how far from the base of the cliff is the height of the projectile maximum. Well, that would be the x of your vertex, or negative b over 2a, which equals negative 1 over 2 times negative 32 over 50 squared. Okay, so once you evaluate this, you can use your calculator just fine. You get x equals 39.1 feet. So this distance from the cliff is almost 40 feet, 39 feet. Alright? Then they want to know what's the maximum height of the projectile. Well, then find what f of negative b over 2a is. Find the height from that. So you plug that back in. So it'll look like this. Negative 32 over 50 squared times 39 squared plus 39 plus 200. And when you work that all out, you end up with 219.5 feet. So our vertex then, which is really what we ended up asking for, was 39, 219, or 220, however you want to round it. Alright, I could ask you, when will it strike the water? Well, take a look at this. We shoot from here. We reach our max. What height are we going to be at when we hit the water? Right here. Splash down. We're going to be at a height 0. So we would set this guy equal to 0 and solve. You could use your calculator for that too. You could hit second calc, and we're going to find a 0 of the function. So I'm going to go left bound here. Go right bound, and I get x. This point here would be right around 170 feet. So this thing would go 170 feet in the air, horizontally, until it hit the water. Alright, so we have a polynomial here, and we want to know the degree of the function. We have factors, what we have is factors being multiplied together. So when that happens, you need to make sure you take all the x's and add their exponents. Or think about what would happen if you multiplied all this together. X times x times x will give you x cubed, so your degree is 3. Alright. We want to find the zeros of the function, and you want to make sure you can find the multiplicity. So I take each factor, x plus 2, set it equal to 0. 2x minus 1 equal to 0, and x minus 3 equal to 0. I get x equals 3, 2x equals 1, so x equals a half, and x equals negative 2. Because each of these factors only happens once, meaning there's no squareds, cubes, or otherwise, then we say that their multiplicities are all 1. So multiplicity of 1, multiplicity of 1, multiplicity of 1. Okay? Then we want to find the y-intercept of this function. Well, we do that just like any other function in the history of mankind ever. We plug in 0 plus 2, 2 times 0 minus 1, and 0 minus 3. So we're trying to find what y equals based off of that. So y equals 2 times -1 times -3 or positive 6. So 0, 6 would be our function there. Okay? If you wanted to know whether or not these touched or crossed, remember that odd multiplicities touch and even cross. So we would say that all of these zeros cross. Alright, so we want to graph that function and use it to describe the domain and range of the function. We have an odd function, right? We had 3 factors, so we have an x cubed. So it's going to look something like that. I know it. The coefficient was positive because there wasn't one. There was no negative sign, there was nothing. So you say the coefficient's a positive 1. You have your zeros at 1/2. And you have a 0 at -2. And you have a 0 at 3. Alright. And I know right from there I'm going to shoot up like that and shoot down there like that. Alright, and then I can plug in my y-intercept. My y-intercept's at 6. So we go 3, 4, 5, 6, and plug that in there. Alright. Alright, so I'm just missing some turning points. So we need to plug this thing into our calculator. So after I plug this in my calculator, I use the calculate button to find my turning points. And the turning point for our max, I find my max at -1, -12, or positive 12 rather, excuse me. Alright, so I'm going to adjust my drawing here. I'm going to delete that. And we're going to give it another shot. We're going to go -2 and 3. And now that I know this turning point, I know this is much sharper than what I'm showing. Okay, and it comes up, comes back down, and then my guess is it's going to keep going like that and go super steep. And so then I need to find my other turning point, and I do that, and I find that it's at about 2, -12. And I just rounded those. Okay. And so then I want to describe the domain and range. Well, remember, we have no vertical asymptotes. So there's nothing that causes this thing to, be undefined anywhere, vertically or horizontally. There's nothing stopping us. So then I can say that y, or our domain rather, is x, provided that x is all real. And our range, y all real. Okay? Okay, now we're going to go backwards. We've got a function. It's got zeros. It's got turning points. It's got a y-intercept. It's got an end behavior that looks odd function to me. Looks like an odd negative function to me. Okay, and so I want to write the function. So I'm going to start with f of x. And I'm going to say that f of x is equal to x plus 1, x minus 1, and x minus 2. And those all came from here, here, here. Okay? We had x equals -1, so I added 1 to both sides to get x plus 1. And then I did the same thing here and here. Alright? Alright, then the only other thing that we need to look at is how does this look once I multiply it all through. So when I FOIL this, I get x squared minus 1, and x minus 2. Then we get, multiply that, I get x cubed minus 2x squared minus x plus 2. Alright, so now we have a function that would have the same zeros. But the problem is that if I plug in 0 for x, I get a positive 2. I don't want that. I want a negative 1. So then I need to multiply this entire thing by something that would turn 2 into negative 1. So negative a half. And then we distribute that through. And we get f of x is equal to negative 1/2 x cubed plus x squared plus 1/2 x minus 1. And there you go. You have your function. Alright. Now you know that you're looking good because negative 1 means your y-intercept, and negative coefficient for an x cubed should look like that, which it does. Alright, we want to take a function like this and be able to find the horizontal, vertical, or oblique asymptotes, and then graph it. So notice that the power in the numerator is greater than the power in the denominator. So m is greater than n, so we need to do long division. X cubed minus, oops, let me spread this out, plus 0x squared plus 0x minus 8. And then we got x squared minus 5x plus 6. So x cubed divided by x squared is x. When we multiply it through, we get x cubed minus 5x squared plus 6x. And then we subtract all that. We get 5x squared minus 6x. 5x squared divided by x squared is plus 5. And when we multiply that 5 to each of these, we get 5x squared minus 25x plus 30. Bring down the minus 8, and you get negative 31x minus 38. So my final answer is y equals x plus 5 minus 31x minus 38 all over x squared minus 5x plus 6. And again, we ignore this. This is our oblique asymptote. We take our numerator, set it equal to 0, and solve to find our vertical our denominator. This is our denominator, bottom number there. So we get x minus 2, x minus 3, so x equals 2, and x equals 3. So I go here, and in red I'm going to draw my verticals. Right there. And then y equals x plus 5. So that's going to have a y-intercept at 5, and then a slope of 1. Y equals x plus 5. X equals 2, and x equals 3. There you go. So then you plug this into your calculator, find some points, find some points to the left of your vertical, in between your vertical, and to the right to get your shape. Okay? Most importantly, you're able to find your asymptotes, and then you plot your points. Alright. Okay, we want to graph the following. Looking at the numerator and denominator, we get m equals n, which means that y equals the coefficients, or 1 in this case, is our horizontal asymptote. Alright. We want to to find the verticals, and we're going to do that by taking the denominator, setting it equal to 0, and solving. X equals plus or minus 2. So we have vertical asymptotes at positive 2 and negative 2. Okay. And then plot some points. Okay, once you've drawn your asymptotes, you want to plot your points. So I started with X and Y. Let me erase this. It's ugly. Okay. And I went -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, and 5. Alright, at -5 we're at 0.38, -4 we're at 0, -3 we're at -1.2, and then -2 we got an error, which makes sense because that's where our asymptote is. At -1 we're at 4, 0 we're at 3, at 1 we're at 3.33. Let's see, going down the list here. At 2 we're at error again, and at 3 we're at 0, and then at 4 we're at 0.67. Lastly we're at 0.86. And then just looking at the graph, we go ahead and plot these. So -5, 0.38, -4, -4 we're at 0, so we're right, oops, let me get my pen, we're right here. At -3 we're at -1.2, and we can see we come along here, hit our points, and shoot on down. Okay. At -1 we're at 4. At 0 we're at 3, and at 1 we're at 3.33. So we've got a parabola in the middle here, coming down, just like that. And then our last guy looks to do the same on the right as it does on the left, so it looks like we got some symmetry here. And so 3 we're at 0, 4 we're at 0.67, 5 we're at 0.86. So we're getting really close to 1, but never going to touch it. Alright, so there's your picture of your graph. I want to make sure that your asymptotes are labeled and drawn in with dashed lines. You got an X and Y chart, and you follow all the steps. Okay, so we're going to multiply. We're going to solve this by algebra. We're going to multiply both sides by x minus 1 and so we get x minus 1 times 2x plus 5 all over x plus 1 greater than or equal to x plus 1. Then we multiply both sides by x plus 1, giving ourselves x minus 1, 2x plus 5 greater than or equal to x plus 1 times x plus 1. Alright, so we get x, when we FOIL this, we get 2x squared minus, or plus 5x minus 2x minus 10, or excuse me, minus 5. So then I get 2x squared plus 3x minus 5 is greater than or equal to x squared plus 2x plus 1. Then I'm going to bring this side over. I'm going to subtract x squared, subtract 2x, and subtract 1 from both sides. So I get x squared plus x minus 6 greater than or equal to 0. So we're looking for x values that would be greater than or equal to 0 to plug into here. We want those intervals. So we're going to start by solving this. We get x plus 3, x minus 2, greater than or equal to 0. So then x is going to be equal to negative 3 or 2. And that's where we start with our intervals. We create our line here, 2, negative 3. So we have our number line. Alright, so then I want to pick some numbers to the left, say negative 4, and to the right, 3. And then I'm going to pick something in between. And I'm going to pick blue. Is 0 there. And again, I'm going to put solid dots on negative 2 and 3 because we're greater than or equal to. Alright, so first let's find out what f of negative 4 would be. Well, f of negative 4 would be negative 4 squared minus 4 minus 6. So 16 minus 10 is 6, so that's positive. And then we've got f of 3. So we got 3 squared minus 3, or excuse me, plus 3 minus 6. So we get 9 plus 3 minus 6 is 12 minus 6, which is 6. So positive to the right. So what we're saying is everything to the right and to the left now looks to be positive. And just to be certain, we plug in f of 0. And f of 0 would leave us with negative 6. So that'd be negative. Which is not what we wanted. We wanted greater than or equal to 0. Greater than or equal to 0. So we want these red intervals. First interval is going to be First interval is going to be from negative infinity to negative 3. And remember, we used a bracket to say that we include negative 3. And then we're going to go from 2 to infinity. Or you could write it as x is greater than or equal to 2 and less than or equal to negative 3. Okay? So both of these work. What that means is that anything within these intervals would give us a positive response or a positive value out, which is what we were asked for in the first place, greater than or equal to 0.